Hello, my name is Joshua Knights, and today I'm presenting the work Wild Places, a large-scale dataset for LiDAR place recognition in unstructured natural environments. In recent years, there have been increasing demands for robotic solutions in unstructured natural environments, for applications such as agriculture, environmental monitoring, and search and rescue. These environments are characterized by dense vegetation, unstructured terrain, and dynamic changes over time due to growth and decay, which pose significant challenges not experienced in more commonly explored urban environments. Some recent datasets have begun addressing this demand for tasks like semantic segmentation or vehicle dynamics prediction, but so far, no suitable dataset has emerged which allows for training and benchmarking the task of place recognition in these natural settings. Place recognition is an essential component of SLAM and autonomous navigation pipelines. Advances in this field have been accelerated by large-scale LiDAR datasets such as KITTI, Oxford, and MULRAM, which are exclusively representative of urban on-road environments. To drive further research into addressing the unique challenges presented by such an unstructured off-road natural setting, we need a large-scale benchmark and dataset with reliable ground truth in such a natural setting. To address this, we introduce Wild Places, a large-scale LiDAR place recognition benchmark for unstructured natural environments. Collected over 14 months in Brisbane, Australia, we use a custom sensor payload in conjunction with the LiDAR SLAM system to explore densely vegetated off-road environments by foot, with an accurate 6-degree freedom ground truth which supports evaluation on both inter-run relocalization and intra-run loop closure detection. With over 63,000 undistorted submaps, this dataset provides a challenging new benchmark for existing place recognition approaches, as we found that many methods which achieve extremely high performance in structured urban settings still have significant room for improvement in the more challenging off-road environments. Each environment in our dataset contains multiple in-sequence revisits and significant structural diversity, transitioning from wide-open trails to densely vegetated canopy, with repetitive tree structures within a single sequence. Our SLAM solution provides point clouds which are both undistorted from motion and extremely dense, with over 300,000 points per cloud. To collect the dataset, we traversed the environments on foot using a handheld sensor payload for data collection. This allowed us to navigate terrain which vehicles or robotic platforms would find difficult or inaccessible, in comparison to existing datasets, which have required roads or much more open trails to support the car or robotic platform carrying the sensor. To generate the global maps and 6-degree of freedom ground truth for each sequence, we use the Wildcat SLAM system. Wildcat integrates GPS, asynchronous IMU, and LiDAR measurements in a sliding window to generate an accurate, undistorted global map. You can check out the original publication for more information. For our inter-sequence ground truth, we align the global point clouds for each environment using iterative closest point, and remove outliers using M-estimator simple consensus. On the left, we visualize the alignment accuracy of the global maps in both environments, with the color bar representing the predicted error of each line point in meters. 95% of points in both environments had an error of less than 0.95 meters, which we believe is more than sufficient for evaluating inter-sequence place recognition. Our dataset supports training and evaluation for both inter-sequence revisits, akin to the kidnap robot problem, and intra-sequence revisits, akin to loop closure detection. Wild Places also contains long-term revisits, i.e. over 12 months, to observe how natural environments can change dynamically over time, and the impact that this has on place recognition performance. While these properties are present in many urban place recognition datasets, to the best of our knowledge, Wild Places is the first dataset in natural environments to support any, let alone all, of these setups. To demonstrate the challenge posed by Wild Places, we benchmark 4 state-of-the-art place recognition approaches and provide training and evaluation splits for the dataset. For our learning-based approaches, we train on the first 2 recorded sequences in each environment, holding out the last 2 for intra-sequence evaluation. Regions marked in red are withheld during training to be used as queries for inter-run evaluation, and regions marked in orange are excluded from the training set to avoid any shared points between the query and training clouds. For our initial benchmark, we select a single non-learning based approach, scan context, and 3 state-of-the-art learning-based methods, Translog3D, Minklog3D v2, and Log3DNet. In the intra-sequence setting, these approaches have all shown extremely strong results on urban place recognition datasets, recording top 1 recalls in the low to mid-90s. But as we show here, they still have significant room for improvement when tested in unstructured natural environments. This demonstrates how natural environments are still very challenging to state-of-the-art place recognition methods, and the value of our dataset as a benchmark to help continue pushing the state-of-the-art forward by addressing these challenges. Again, in the inter-sequence setup, we see how the top 1 recall in natural environments has significant room for improvement compared to the mid to high 90s we often observe in urban datasets. We also see that when we compare the inter-sequence performance for two sequences collected on the same day compared to two sequences collected 6 or 14 months apart, there's a huge drop in performance, which shows how the changes that occur over time in natural environments can present additional challenges for long-term relocalization. In our future work, we also plan on releasing camera frames and both point and pixel semantic labels for the dataset, to encourage further exploration of visual odometry, semantic segmentation, and the potential synergy and interplay between these tasks in natural environments. Thank you for listening to our presentation. For any questions or inquiries, please visit our website using the link or QR code given here, or contact the authors at the listed email addresses.